Thank you for having me. Again, I'm really excited to be seeing all these communities come together. So I'm taking a sort of a different approach from our last talk about trying to understand water and how atmospheres affect that. So this is a figure from Darby Dyer, and I really like this figure because it talks a lot about basically the presence of water that we think may or may not have been on our terrestrial neighbors early on. So at Mars, we have a number of assets there, as you well know, but we actually think that the presence of liquid water was not all that long in terms of the full geological history, so maybe 500 million years ago. At Venus, as we heard earlier, that really high D to H ratio and a number of other factors go into our belief that we think that the presence of liquid water existed for quite a bit longer, and at Earth we know it still exists today. That's coupled with the fact that we also think that the volcanic activity, so a source for that atmosphere, may have existed in really different time periods as well. Mars being, we think that it was not as volcanically active for as long as, for example, Venus and then Earth. So today we're going to be talking a lot about how the atmosphere has evolved and how it has over time. And again, this really ties into understanding the presence of liquid water on a planet. And everything we're going to be talking about today is going to be that post-hydrodynamic, post-bombardment period. So I'm ignoring that really, really early cataclysmic period in terms of atmospheric and planetary formation. Okay, so we know that Earth and Venus have this really thick atmosphere capable of sustaining liquid water. But we also know that unlike Earth, there we go. Mars and Venus lack an intrinsic planetary dipole magnetic field. And Mars has this sort of hybrid system, so it has these remnant crustal magnetic fields. And so one of the talks we'll hear about tomorrow, in fact, I think there's a whole session on it, is trying to understand, does that actually shield or does that actually facilitate atmospheric erosion? But the things that we really want to focus on today in terms of the history of atmospheric evolution at Mars and Venus have to do with these escape mechanisms. So at Mars, genes escape, photochemical escape, and ion escape are all taking place today, currently. And actually the main channel for atmospheric escape at Mars is through photochemical escape, which we'll talk about in a minute. At Venus, however, the main mechanism for escape is ion escape. And that's because the gravitational well is much higher. So neutrals do not efficiently escape today at Venus. And that's an important comparison when we try and think about how these two planets have evolved differently. So when we talk about genes escape, just as a brief reminder, we're talking about the loss of particles from that energetic tail of the speed distribution. And typically these are going to be our lighter elements, things like hydrogen. So, and again, this is that post-hydrodynamic escape. So for effectively, 3 billion years and on until today, genes escape, especially at Mars, is definitely taking place. In terms of photochemical escape for the neutrals, what you can basically have is dissociative recombination of O2+, which is pretty dominant in a CO2 atmosphere. And again, at Mars, this is an incredibly efficient way for the atmosphere to actually be escaping. However, at both these planets, ion escape is taking place. And this happens when that neutral upper atmosphere is ionized by the impending solar wind and the magnetic fields that come with the sun. And so basically what happens is these ions, these neutrals become ionized, and then they sense the electric and magnetic fields, and they actually get picked up and swept away. And so this is, again, one of the main, certainly the main channel for atmospheric escape at Venus today, and exists at Mars as well. Another thing to quickly point out that I didn't put 100% in there, ions can escape, but they can also precipitate back. Basically, on that first gyration, what can happen is they can precipitate into the atmosphere, and this is called sputtering. So you can have all these different ions crashing back into the atmosphere. And this is sort of like if you throw a penny in a pond, you'll get a little splash. But if you take these really heavy ions, you're going to splash the whole pool out. It's like doing a cannonball in a pool. This is an incredibly efficient way to remove neutrals from both planets. And we'll talk a little bit about that in a minute. Either way, ion escape and the sputtering, so that from ion precipitation, are driven by the solar wind. And that's really important. So we just sort of talked about this in the last talk, but we know that the earlier sun was rotating faster than it is today. So whether it was a slow rotator or a fast rotator, it still was rotating faster. We know that certainly because as the solar wind is, accreting off the planet, it's losing angular momentum. So either way, we had a much stronger XUV, and we had much stronger solar wind. And that's, again, really important because the solar wind is what's driving two of these really important processes, both the ion escape and the sputtering. And not to mention, the sun was much more active. And so we have a lot of reason to believe that not just do you have more solar wind, you're having a lot more solar activity. So things like your coronal mass ejections and those stream interaction regions, often called CIRs. So here we are in today's solar cycle, and this is solar cycle 24, and here we are just beginning in solar cycle 25, which are relatively quiet. But if we look at the missions over the last couple of solar cycles for Mars and Venus, this is what we're seeing in terms of, and again, this is going to be mostly the plasma observations. So here we see PVO, that was during solar cycle 21 and 22. We had VEX, which is Venus Express, so that was more recently over solar cycle 23 and 24. And then we have had a slew of Mars missions, so MGS, Mars Express, and MAVEN over the last few solar cycles. But again, it's important to look, we're seeing really different missions across different solar cycles. And again, this is that sunspot number, which is a tell for how active the sun is, how many CMEs and CIRs and things like that, how often those things are happening. So MEX and VEX in terms of the ion escape, historically what we've learned, these have, again, that similar, it's not quite cometary. You're seeing a lot of really interesting structure in terms of the ion escape at both Mars and Venus. And Mars and Venus, these were with ESA missions, and so they had very, very similar instrumentation. So this is a really nice apples to apples comparison of the kinds of ion escape we're seeing at both planets. Incidentally, Venus, we're seeing about an order of magnitude higher ion escape than we did at Mars. MAVEN has also observed quite a bit of ion escape, but in terms of some of the newer science we found out, we've learned a lot about photochemical and sputtered escape. So photochemical escape through IUVS, we've learned that is the dominant atmospheric escape process at Mars today. In terms of sputtering, we've been able to look at isotope measurements, especially of argon, and then looking at that separation in the homopause, we're able to determine that effectively around 65% of argon has been removed from sputtering. And again, argon is inert. So we know that the only way for argon to really efficiently be removed is through something like sputtering because it doesn't ionize very easily either. So we have all of these. So I think Mars we have a better handle on because we are starting to understand photochemical escape and ion escape and some of that sputtering. But at Venus, because we had PVO and VEX over really different portions of the solar cycle, we see a really strong, a huge range in some of those escape rates. So this is the O+ per second escape rate. And I mean, that's not a reasonable number to tell you like what's actually happening. So perhaps a better way to think about the escape rate is in what we call the global equivalent layer of water. So that's where we take an escape rate and we say, okay, if the whole planet was covered in water, how many meters of water would that be? And here you're seeing these are the escape rates that correspond to the meters of that gel water layer. And so you can see we're talking anywhere from a fraction of a meter to actual meters. And so at Venus, it's really important for us to start constraining the escape rate in a better way, especially as a function of solar cycle. And again, as we talked about in the last talk, this has a lot of limitations for some of that crustal oxidation and, where did the water go at Venus? So in terms of the space weather, we also know that space weather now, and especially when the sun was much younger and much more active, was a huge driver of atmospheric escape. So this is a September 2017 simulation of a huge set of space weather events. And here at MAVEN, we were able to see all these really nice signatures on both of a flare and a CME. However, you'll see nothing at Venus, no assets there. That would have been great because it was right in line to have seen this. I'll play that one more time in case you missed it, in case I'm not being subtle enough. So it would have been really great to see something there because at Earth, and at stereo A, we were able to see these signatures of this, arguably one of the biggest solar events of solar cycle 24. Nope, there it is. So this is some work I did with MAVEN looking at just as a function of the escape rate. These red dots here are just these red numbers. That's the flux during space weather events. so things like CMEs and CIRs, and everything else, these are just all of the other orbits. So when you look at the average loss per orbit, you can see that the space weather events are really driving ion escape in particular. So this is a figure from Dave's brain, and what we want to do when we think about how do we take all of these numbers and put them together to understand how much atmosphere has been lost over time, we take our present day escape rates and we can constrain them from isotopes. That helps us tell us what's the maximum amount of atmosphere that could be lost. And then we take these extreme solar events, these CMEs and these SIRs and such, and as a function of an increased solar activity, we can try and back out how much atmosphere was lost. These are like the top 5 assumptions I can make. There are tons of assumptions that go into what I'm about to show you, but certainly we are assuming an increase in the XUV and EUV as well as the solar wind. Things like the CMEs and CIRs most likely were much more common earlier on. There also the earlier atmospheres have to be based on GCM models with an increased EUV. And again, as always, this is post-bombardment and post-hydrodynamic. So when we give these what we think to be these estimates of atmospheric loss over time, take it with a grain of salt because all of these really depend on models and the data we're taking. And so at Mars, what we've effectively taken, you can take your pickup, your ion escape rates, sputtering, and this dissociative recombination is photochemical escape. And if you take all of those at different time steps, here we did this with 4 different time steps. This is the equivalent of around almost half a bar of atmosphere, or that global equivalent around 11 meters of water. At Venus, it's more, although I should point out at Venus, when we first did this, I thought it would be significantly more because it's closer to the sun, it has a much stronger solar wind, and it has more atmosphere to lose in the first place. So when we look back in time, right around here, at Mars, we're seeing it lost quite much more atmosphere. So like the percentage of its atmosphere starting, it lost quite a bit. So in terms of future missions, just to quickly go through where we are going forward and how we can measure atmospheric escape, ESCAPADE is a simplex mission going to Mars. It's a twin-sat looking at particularly that ion escape again. And then we have things like EMM, which is going to be looking at some of the photochemistry at Mars. And then we have, I've put Parker Solar Probe, Bepi Colombo, and Solar Orbiter. They're not future missions to Venus, as you well know. However, they have Venus flybys. And so I sort of like wrangled my way into getting everybody to turn on for at least a Solar Probe Venus flybys. So this is just a quick plot of looking at, these are the past and present observations at Venus in terms of plasma. So here, this outside, this is PVO, that was around 1978 to 1992. And you can see, this is a top-down view. You can see its orbit, this is around a 24-hour orbit, and it's going out to about 12 RV. Then we had VEX from 2006 to 2014, and then a handful of flybys. And these are the first 2 Venus flybys, or gravity assist. So first of all, there's low-hanging fruit. This is a region we haven't explored before, but we're also seeing a really interesting region in terms of how the solar wind is interacting with that atmosphere. Just as a highlight, so again, this is a top-down view. So this is the solar wind interaction, and then this is that magnetic field, the interplanetary magnetic field strength. Here are all the different flybys, and you can see that this 3rd and 4th flyby, as well as 7 and Fuchsia here, are going to be awesome. They're cutting right across the tail here. And I'm really excited for that because while we don't have a Venus mission right now, we do have some hours of data. And I will take something over nothing. So first of all, if anybody is interested in seeing some of this data, please come find me after. But again, we're able to turn on for all of this. And we're also hoping that Bepi Colombo and Solar Orbiter are able to use their instrumentation to observe Venus as well. Bepi Colombo has 2 flybys coming up, which are, one is in October and then one is about a year later. And then Solar Orbiter, which I think is now February 9th is the delayed launch date, but that actually has 7 different flybys. So if you know anybody on the team, pressure them. And so one of the things, the really cool things since Solar Probe, we've convinced them already, we're going to be observing, these are the Venus flybys as a function of that solar cycle. And so to sort of bring everything back, we know that the main way Venus's atmosphere is eroding today is through ion escape. And ion escape is very, very dependent on the solar wind in those conditions. So what's really cool is that we're going to get 7 chances to observe that atmosphere over a solar cycle, since again, there is nothing in the lineup today. So just to conclude, we had PVO and VEX and MEX and MDS and MAVEN. So we have had quite a few in-situ observations of these atmospheres. However, we really need future missions, especially at Venus, to make sure we understand what that atmosphere is doing today, especially because it has so many keys to understanding water and just how this atmosphere has evolved so differently. And certainly that has the obvious link to exoplanetary atmospheres. And then again, solar probe, and then hopefully Bepi Colombo and Solar Orbiter can help us provide more of that data. So thank you.